Just always, I mean, the dinner was great, and that's always a good sign of a good conference. But I think it's also what I call the storyline of the program itself. So when we started early on with Axel, you know, and then now we're here at this, you know, talking about how X-rays and magnetism can really be used to do imaging. And we just heard early on, I mean, the last question that we heard in the previous discussion was just leading into this. To me, this means you really put a lot of thought into make this Trends in Magnetism a fantastic conference now, and I'm hoping I can contribute a little bit to this. So this is now about, in this overarching field, antiferromagnetism and light. So now we pick the magnetism and X-rays, and particularly we want to do imaging. This is now the topic of this session here, and since I'm the first one, there's three others after me, I thought I should do first also a little bit of a broad introduction, a little setting the stage, so we can just then move on and then see how this field is really developing and growing, and then finally at the end we'll see, you know, where it's going in the final discussion with this. That's, I think, what I'm hoping can do here. Okay, so I will talk, although I switch a little bit, I have to say this was a conference where so far I was not totally dominated about skyrmions. I mean, there might be a reason for this, but I will also show you what we're doing right now to go in beyond the skyrmions. And this goes also back to increasing dimensionality. We want to go into the third dimension with these topological spin textures. And I will show you our results on hopfions particularly that I feel is a new direction that this field will be going. I want to start first, of course, thanking the funding agency, which is the Department of Energy, and I'm funded by the Non-Equilibrium Magnetic Materials Program, and this name itself also tells a little bit, I think has a lot to do with this conference here, so this is great for me to be here. Okay, so quick overview, I'll talk about magnetism and X-rays generally and how we can use it for imaging. And then I will show you some results recent that we've done with topological spin textures, particularly when we go from a two-dimensional spin texture to the three-dimensional spin texture. In the three-dimensional, we'll see there's new opportunities, there's completely new, you know, challenges out there that allow us to really do something that you cannot do in 2D. And then finally, going to the fourth dimension, because there was also a question about the dimensionality, and I think Claire will also probably talk about this, we also need to understand the dynamics of all these spin textures. Because in the end, any function, there's a lot of questions always about how we can use all this. In the end, any device is an action. There's something going on. You never look into a static piece that will not do anything for you. So it's also the dynamics we need to understand. And this is what I'm trying to I hope to show you towards the end of my talk as well. Okay, so very briefly, I mean, why are we looking into spin textures? I think spin textures in the end, how the spins align, is the foundation of understanding magnetic materials. And as you all know, I mean, there's 3 and probably in the future even 4 classes of materials we'll call the magnets. The very traditional ones, collinear, given by a symmetric exchange interaction, where you have basically neighboring spins coupling parallel. We all know this, and this of course gives rise to both the ferromagnets, the antiferromagnets, as well as the ferrimagnets, and we also talked a lot about this here in this symposium, in this workshop. Then of course, when you bring now a cross product between 2 neighboring spins, which is again this antisymmetric exchange interaction, you arrive at non-collinear spin textures. And now the whole idea is when you talk about these magnetic materials here, you just play with those 2 interactions to start with, a linear, a collinear, and a non-collinear, and you end up with completely new materials, new spin textures that come with new properties, behaviors, and we just tune those different interactions. Broken inversion symmetry, as we heard many, many times here, is one of the keys, but interfaces equally, I think, is very important. And here's just one last topic here, don't talk about this today. Maybe the local curvature itself might even allow us to play with the spin textures on a small scale, and this is something which some of you might be interested in, curvilinear magnetism, and just bend them on a curved surface, things like this. Okay, so now, this is now my summary slide here of X-rays are really a powerful tool for magnetism, and I put here in red, this is really about elemental specificity. I mean, the X-rays are uniquely appropriate to look into one component, and what we heard earlier today about, 2-color experiments, things like this. I think I cannot imagine any other real probe that could do this in a similar, easy way, and you've heard already a lot about this. I just want to sum up here a little bit. One is, of course, for the mostly ferromagnetic systems. This is the X-ray magnetic circle dichroism effect, and you know all this. I mean, this is when you use circular polarized light from an X-ray source, storage rings, or free electron lasers, and you just basically take advantage that the absorption, the reflection, the transmission, whatever, changes as a function whether the magnetization is pointing parallel or antiparallel to the velocity of the photons. That gives you then the XMCD contrast, and we've heard Quentin Lucia talked about. I mean, this has been around here many, many times. In the end, it measures the expectation value of the atomic magnetic moment. Again, this is elemental specific because those binding energies are specific to the atomic structure here. You also, and that's very important when it comes down to what do we learn from all of this, why I'm just measuring this, we can also quantify it in terms of applying the sum rule, spin moments, orbital moments, and this has been done early on, where then now by just basically measuring kind of the areas under the spectroscopic profile, and you're able to really determine elements specifically spin and orbital magnetic moments. Now, this is what this conference is probably most interested in, the X-ray magnetic linear dichroism. And again, you see here this arises from a non-spherical charge distribution. It was already pointed out earlier today. This measures basically the expectation value of a square of the atomic magnetic moment, right? So, I mean, and of course, this is primarily used for antiferromagnets, although to some degree, you might even be able to do this for ferro and ferrimagnets, but since the XMCD is so strong, I think most of the community is just basically using XMCD for doing this. So this is now, in a nutshell, what is the core of all these X-ray and imaging techniques in the end. And now, of course, how we do now the imaging, there's, I would say, two different routes that the community has developed over the last, what is now 20, 25 years or so. One started off just when you think about imaging, I mean, what are you doing if you have no idea what a microscope looks like? You just try to do a real space image because you want to get some real images there. And of course, it started all with Joe Stir, 93, I guess, using the PEAM microscope back then and looked into samples, I believe back then was IBM, and was able to use these surface-sensitive PEAM technique, photo emission electron microscopy, to take an image of a sample. And then we did, a couple of years later, looked into more zone plate techniques. There was, of course, both the full-field transmission microscope as well as then the scanning transmission microscope, which are now really workhorses. All of them, I would say, are workhorses around the world. If you're I would say, layperson in doing this, just reach out to people or the experts, say, here's my sample, what can I do, and how can I actually image those kind of spin textures there. And then, and we'll hear more about this, I think, in the upcoming talks, these reciprocal space imaging techniques that also use X-rays, but now instead of going with some optics into a real space imaging, they go to reciprocal space, and then you basically retrieve the information from there, and we'll hear probably a lot more from Claire and others later on. And there's a couple of them I just want to highlight. There's a whole zoo of techniques out there, but I really want to say, maybe it started off a little bit with Stefan Eisebitz's X-ray holography, which I think was a fascinating experiment back then in 2004, where it's, again, the counterpart to holography that you know from optics and was just brought into the X-ray regime. Then, of course, later on, there was, people thought about the X-ray tychography, which is basically you use a scanning transition microscope and you take just diffraction images, thousands of them, and just do this oversampling, and you reconstruct from that then the images. And then quite lately, I think we'll hear probably from Claire, the X-ray laminography, which again is another way that allows us also to do multidimensional kind of spin imaging of spin textures. And I just want to point out again, I'm really very, impressed by two color modes in holography. We have single shot capability using a free electron lasers. And this is just one example, again, I think from Stefan Eisebitz's group, using a cobalt platinum multilayer, and at the same time with the one source, you basically take two images of two different elements, single shot. That's, I think, a beautiful new opportunity for the future. And I think it was even done at the LETRA here, right? So not too far away. We come back to Venice, fly for beam time, and just keep doing this. Okay, in a nutshell, these techniques, they all, I think, in principle, because of the wavelengths of the soft X-rays in particular, will bring us down into nanometer regime. Whether we're there today, I wouldn't claim that, but at least in principle, we should be able to bring it there just because of what a diffraction limit of imaging there is. The temporal resolution, and that's now, I think, a key thing here as well. We can really reach from femtoseconds if we go to free electron lasers to nanoseconds. So it really covers across scales of time scales. Whether it's a pump probe, single shot, or more recently, fluctuations, what you might think is a noise in the spin dynamics. There are now techniques out there, for instance, at the LCLS, the 2-pulse XPS, where we were able to study fluctuations of spin dynamics, of course, on a nanometer length scale. And it's pretty interesting what you can do with this. This, of course, has to do with the coherence of the light source now. The fact that more and more synchrotrons and XFELs are in the end providing fully coherent X-rays. This, I think, will be transformative in allowing us completely new experiments in the future, particularly when it comes down to fundamental studies of magnetic materials. And again, the spectroscopy I mentioned already is always inherent element specific. So that's, in a nutshell, what you should keep in mind when you do this. Okay, now this elemental specificity, an example I just want to share with you very briefly. We've done this a couple of years ago. We just looked into a simple core platinum system. I believe the sample came from Andy Kent. I'm not quite sure anymore. Anyway, what we did is we did a full imaging spectrum. So we took images across these XMCD energy scale. And then I asked my student to analyze the data to see whether there's any changes happening at domain walls as a function of the spectroscopy. And what he came up with is that the L/S ratio, again, this was analyzing some rules, seems to be somehow modified, reduced at the domain wall. And we had no idea why all of a sudden the spectroscopic signal would just change because of the spin texture there. But we thought, well, there might be some very complex spin texture domain wall, some rearranging of some orbitals that might be doing this. But anyway, the key here is to resolve this problem, finally, we just have to do a 3D tomography of domain walls. That means with a nanometer spatial resolution, look inside the domain wall and understand what is the spin texture look like there. Okay, now let me come to topological systems, because that's really what kept us very busy for the last 10, 15 years now. And I just want to give you a brief history of this, how it all started. It really started off with vortex structures, that famous paper, of course, from Jinzhou and others using MFM, and they were able to see in these permaloid disks these very nice, little black and white spots in the center, science paper. And this, I think, triggered off a little bit. So you have a spin texture that follows the shape that gives rise to a circularity, or chirality, some people call it. That could be clockwise, counterclockwise, and in the center, of course, due to energy constraints, you have to have, finding the shape anisotropy, and you come up with a polarity. That means there, the magnetization pointing up or down. So you have in one unit, in the end, 4 different directions that you can play with, 4 different degrees of freedom. People got excited about this. Should we use this for a 4-bit, whatever, computational thing? And then, of course, about 10 years later, or so I would say, we started looking into skyrmions, where now, and we heard about this, the magnetization actually from the left to the right edge makes a full rotation. It's characterized by the skyrmion, the topological winding number, where you basically have really going 1 for the skyrmion. A lot of excitement, seen to be a potential candidate for low power, fast, small racetracks and things like this. And a lot of work is going on still now. I think it's fascinating work because all of a sudden you have the topology. But then just a couple of years ago, maybe even 10 years later again, the field switched again. And all of a sudden people thought, okay, what is a skyrmion? It's a 2-dimensional system. But in the end, we're looking into, let's say, a layer system of 50 nanometers or so. Will this skyrmion texture really go all the way through? Is it just a rigid kind of a tube that goes through? And all of a sudden, people started realizing, well, we probably have to look into the 3-dimensional full content of this skyrmion texture as well. And then this is where finally you could arrive at the hopfions. Just imagine, take a skyrmion through a thick layer as a tube, start twisting this tube, band it together, and this is in the end what you have now as a cartoon, as a model of such a hopfion, where you can see now these different colored lines. Actually, it's just how a component of magnetization is just twisting or running around basically this torus line. This, I think, is in the end, and this is something that you can only achieve in 3D. There's no way you can sit down tonight and think about, can I do this in a 2-dimensional arrangement? I think it's impossible, right? This requires, of course, a 3-dimensional kind of consideration. And the topological number there is the so-called linking number. And now let me just give you a little side note. What happens to your group meetings when you start talking about topological spin textures? I think you all have seen this analogy that a donut and a beer mug is topologically the same, right? Because you can just deform it from one into another. So when I had my group meetings, I always brought the donuts when we talked about skyrmions. And since we talk about hopfions, we brought a different pastry. It's a cinnamon twist, right? And in the end, I think, just eating this and talking about the science, I think you get some ideas about what's going on. Anyway, and this is, of course, now linked because there are now these individual lines are linked to each other. And this is, again, there's 2 cups that are just linked together. Okay, so now this is about antiferromagnetics. And I thought, what has been done in antiferromagnetic topological spin textures? I want to highlight a few of the work here. The one here, this was from Oleg Tretyakov and others, who really said an antiferromagnetic skyrmion is basically a compound topological object. that has similar opposite spin signs on each of the sublattices. Now the interesting thing, I'm not sure we can see it, it has a complete cancellation of the Magnus force, and this is very interesting in a racetrack geometry. You'll see later on about skirmins. Normally they just get the Hall effect and they're just getting pushed to the side, which if you want to use them in a racetrack, it's not going to work. So you have to think about something else. Maybe the antiferromagnetic skirmins might be a way to do this. And then another paper from here that showed some antiferromagnetic half skyrmions. Again, people talk about various topological objects. This group was able to stabilize merons, antimerons, bimerons in an antiferromagnetic iron oxide. They did precise tuning of exchange and anisotropy. Again, all these topological synthesis is about you have to fine-tune the competing interaction, and they finally get what you want. They were able to show about 100 nanometer small sizes. They could erase them magnetic fields and brought them back by temperature cycling. And here they used already XMLD, linear diagrams and PEAM, to image those various antiferromagnetic spin textures. Then another one, I just want to point out here, a room temperature stabilization of antiferromagnetic skyrmins in synthetic antiferromagnets. Again, it's about tuning PMA, coupling, and chiral order in a bias layer synthetic antiferromagnets. And they used now not X-rays. I still think it's important work here. MFM imaging shows antiferromagnetic skyrmins, and they predict that they might be able to bring them down to really, really small, like less than 10 nanometer sizes. So again, the idea, the hope from using skyrmions, small, fast, low power, I think this field is trying to move into this direction. Okay, and I couldn't resist during lunchtime now to also bring this up here. I'm not quite sure, you probably know more than I, but I see some keywords here like topological matter, Barry phase, and so I would not exclude that in the future we're also looking into, the altermagnets and think about, hopfions in altermagnets, but to be seen, maybe a couple years down the road at this conference here. Okay, so then, of course, I'm not the only one think about how we bring the skyrmins to 3D, and there's some very interesting work I just want to highlight here as well. This is work where they looked into the skyrmion tubes. I described them early on. Using a combination of resonant magnetic X-ray diffraction and holography. And what was interesting, this group found basically at the very bottom there, Bloch points. And you will see throughout the following slides now, there's quite often these Bloch points, vortex rings, and things like that are very characteristic of these three-dimensional spin textures. And of course, this is a lot of exciting science that we can study now with this. Then this one here, this is not X-rays. I also want to mention it here. There's more than X-rays if you want to do imaging. This is a study by the Jülich group looking into chiral boppers in iron germanium systems. They used electron holography. So again, what I'm saying is X-rays is not the only tool that you can use for all of this, but they have a lot of advantages. And they were able to finally, again, show from skyrmon tubes applying a certain magnetic field sequence, and they were able to do this chiral boppers. Again, at the very bottom there at the apex, there's a Bloch point. Again, very interesting science that you can do with this. And finally, again, the recent cocoons, skyrmionic cocoons that are created, fabricated by a single gradient magnetic multilayer system. And they found, using, again, MFM, very characteristic ellipsoidal shape signatures in the MFM. So again, what I'm saying is there's a lot going on in the three-dimensional kind of topological spin textures, but I'm asking the question, is there something beyond the skyrmions? And now I'm coming back again to the hopfions that I introduced early on. And this is a theoretical paper from Paul Sutcliffe, who really got me thinking about all of this, I have to say. And there was numerical computations that says frustrated magnets might be able twisted loops of skyrmon strings, and they can be formed to stable new three-dimensional nanoparticles magnetic hopfions. So the bottom line of this slide here is basically, I think we are able to design our three-dimensional topological spin textures in the future. Okay, and then what really got me going is this paper from Paul Sutcliffe, where he finally said a mechanism to create a hopfion is from a target skyrmon introducing interfacial perpendicular magnetic anisotropy. So the recipe is you design your perpendicular anisotropy across the layer, and you will be able to stabilize a magnetic hopfion in a system. Okay, so we had to go first through the target skyrmion system. What are target skyrmions? Well, these are composite skyrmions, and they have been already introduced many, many years ago. Alex Bogdanov and Alex Hubert, 1999. They talked about n-pi vortices with multiple rotations of the magnetization. So this would be a regular skyrmion, one rotation. Here would be 2, 3, and so on and so forth. So how do we make them? Well, we said, why not imprinting vortex structures that we studied for many, many years on permalloys and imprint them into iridium cobalt platinum layer, which we knew generated some skyrmions. And then what the key was here now that we used the penetration power of X-rays and the elemental specificity to look underneath these permaloid discs where there was some imprinting going on from this vortex structure into this DMI material, and we were able to finally see concentric rings here that are closed, and there were indicators or proof that we have seen target skyrmions of various rotations of the mechanization. So for instance, this one here, this image is one rotation. This one here had 1, 2 circles, that's 2, 3, 2, 3, and 4. So up to 4 pi rotations we found in the target skyrmions. And we said, great, now we have a recipe, now we can start looking for hopfions because we know how to make these target skyrmions. And what would be now the difference? So how do we actually distinguish now the target skyrmion from the hopfion experimentally? I think that's a key message here as well. The target skyrmion, when you just look, and this is a cartoon here again, when you look across the thickness here, you will see the spins are all the same. That means if you look through with a bulk sensitive technique, you wouldn't see any difference. But the hopfion, because of its spin texture, would have a different spin texture at the surface versus the bulk. So now, we're going back to my overview slide, what kind of technologies you can use. Microscopies, we have one, which is the PEAM, that allows us to look at the surface. We have one that is the full field. They're both full field techniques, actually, and we'll look through. So now we take actually 2 images, same sample, same contrast, same resolution, do two images and compare them and see is there a difference. For the target skyrmions, we should not see any difference. For the hopfions, we should see a difference. That's what I ask my student to do. Go out, take these 2 images, basically, and come back, show me are they different, are they the same. That's what we did. But first, to get there, we had to, again, go back to Paul Sutcliffe and say, Paul, what do we need to do? How is our PMA profile? How does it look like? And he made some simulations and calculations. In the end, that's what he came up with. No matter, I mean, there's a certain recipe how you do this. You make the cobalt layer and a platinum iridium cobalt a little thicker or a little thinner, just shape it, and then you generate a PMA profile that looks either straight, that would give us the target skyrmion, or you do it differently, you would get something that looks like a hopfion. And then we did even more some expectations, what to expect before we go to the synchrotron. How would a PEAM image look like for a target skyrmion and the MTXM? Of course, not surprising, they would look the same, but here's now the key. The PEAM image, particularly for a hopfion, would look drastically different. So that's what the signature we were looking for. And as I said, we went there, did the experiments, we even rotated, and we saw it earlier today as well. You can rotate a PEAM image, and you finally get a full 3D reconstruction of the PEAM images in the surface. And this is what the simulation here, the experiments. So we had now a clear signature of a hopfion. Again, the MTXM looked as expected as well. And then we also compared how it looked like for the target skyrmion. Just look at those, and look at those. Totally different. So it was very clear this is an hopfion that we have stabilized, not surprising because it was predicted by theory. I think we controlled well our synthesis capabilities, so why would all of a sudden all of this just fall apart? But I think it was a clear, nice combination of 2 different X-ray imaging techniques that allowed us to finally prove we can stabilize a hopfion. And the toron, I just mentioned it here, that's another topological spin texture, because you will see now in my next slide when we go to dynamics of hopfions, field-driven dynamics particularly, there's a transition from a hopfion to a toron. So again, this is for us now the next direction to go for. Coming now to the dynamics, and I'm almost done. The skyrmion Hall effect that I mentioned early on for skyrmions, where you deflect when you go along a racetrack, can be actually bypassed or would in certain cases not exist if you have a hopfion, because there's a gyro vector, and the hopfion should have 0 net gyro vector, basically because you have 2 skyrmions that are kind of clockwise, anti-clockwise. That means this balance is what some people try to do with artificial antiferromagnets. You can do it actually in this spin structure itself. You balance it out, and it just means you can just move straight forward. These are papers from Arne Bratasch and Jialong Zhang who actually predicted that, and they also had some prediction simulations about what would current-driven dynamics look like, what would be spin transfer torque-driven dynamics look like. There's a lot of simulations out there. So far, I think we're ready to go do experiments and finally prove that all the simulations are correct. That's, I think, of course, the next step to do. And this is what my student did during COVID, because we're not allowed to go to the synchrotrons. And I asked him, well, normally you do the simulations afterwards. Let's do it first, and then just predict a little bit what's happening. And here you see a plot of the total exchange energy as a function of applied magnetic field, because we wanted to study the hopfion dynamics under the applied magnetic field. Yes, that's one thing to do. And as you can see, there's at a certain applied magnetic field, there's a drop of these total exchange energy where it goes from a hopfion to the toron. And here is also some simulations, and as you can see, this kind of cinnamon twist structure actually collapses, and then finally when you have the toron, you see this. Now this is the analogous spin texture of toron. Do a little bit more about the simulations. How would the frequency spectrum look like, spin wave resonances? This was the pulse that went in, and here you can see nicely, again, the frequency goes from 5 to 15 gigahertz across a certain field range here, and you see this very sharp line here. On the left side, there are spin bands or spin wave resonances that are hopfion, from hopfion spin texture, and right here, there's the toron one. So if we now do time-resolved MCD measurements, we should be able to sit, let's say, on one of the frequencies here and then go across here. Maybe, you know, if you do it right, we should also be seeing then simulating the transformation from a hopfion to a toron and understand the dynamics there. And this also would allow us to do some, spatially resolved. Again, this is very demanding. I would say we have to go really to 3D dynamics, four-dimensional. Yes, I'm almost done. So, but I think this is another just open challenge for the future. Can be now tomography of dynamics in those hopfion to toron transitions as a function of magnetic field. I think we should be able to, study all that, and there will be a lot to learn because, particularly, as I said early on, there's quite often these Bloch points involved, there's vortices involved, so you can really understand now all of a sudden these dynamics of these very special kind of singularities, particularly the Bloch points there in these topological spin textures in 3D. Okay, now let me sum up a little bit my talk, and then we have time for some discussion. So I hope I could give you a little bit now launching the field here for the next 3 talks as well. Magnetic X-ray spectromicroscopies that use both XMCD and XMLD, I think are pretty unique and pretty powerful tools to allow us to study all these different magnetic materials and the underlying spin texture. In the end, we need to understand the spin texture and its dynamics to finally understand properties, behavior, and functionality. And the thing is, we can really, I think, we have now made it to multiple dimensions. 3D tomography is there, including, I would say there was a discussion early on about interfaces. I mean, interface itself is a 3-dimensional kind of aspect to this. And whether we go into a reflection mode geometry or whether we just do a full 3D, reconstruction, I mean, you will see the interface, and then you go to the computer, do the slices. And also this curvature, I think it's an interesting parameter to play with, particularly when the radius reaches fundamental exchange lengths. I think you will see some interesting phenomena coming up. Ultimately, of course, all these extras will go to fundamental magnetic lengths and time scales, but I think it's important to stress we can also go across scales. So we can probably follow the dynamics across from the femtoseconds all the way up to whatever, nanoseconds. And this, I think, is important as well. New capabilities, of course, and I think we'll probably hear more about this in the upcoming talks, because of this full coherence of X-rays, and we heard already a couple of talks at this conference here. Interferometry, X-ray interferometry, just imagine what you can do, what has been done in science with interferometric capabilities. Now just think about this to be done in magnetic materials with the same precision. I mean, this is just a wide open field. Phase-sensitive imaging, I'm pretty sure this is one of the knobs to turn when you have the phase instead of just the amplitude. Now, of course, I showed you quite a few of those non-trivial topological spin textures that emerge in 3D. A lot of scientific new directions will open up, but it's really challenging both to make them, to characterize them, and also the model and the theory. I think it still needs a lot of work to do. And I showed you then 2 examples. One was the hopfion statics, where we used 2 separate characteristic techniques to allow us to quantify the 3D spin texture. Finally, so far only the simulations, but they indicate very interesting dynamic behavior. Of course, waiting for experimental verification. Hope next year I'll be able to show you more of this. These 2 students were really key. He did the static one. He's now still working on the dynamic one. And then we talked a lot about the upcoming conference. I think great to come back to real conferences. This is already next year. This is the 11th International Symposium on Metallic Multilayers in Korea. So if you haven't seen the email yet, write it down or go there. I think it's a beautiful conference. Anyway, with that, let me thank you all and happy to take any questions.